question number 105. Flexural rigidity is the product of dash with usual notation. Option A, E and I. Option B, C and J. Option C, K and J. Option D, C and J. So flexural rigidity. We know that flexural rigidity is the product of Young's modulus or modulus of elasticity and moment of inertia. Moment of inertia. So Young's modulus is denoted by capital E and moment of inertia is denoted by I. So the product of E and I is called flexural rigidity. So option A, E and I is the right answer. So the flexural rigidity is the product of Young's modulus and the moment of inertia. Look at the option B where C and G, C and J. C means the rigidity modulus and J is a polar moment of inertia. In option C, K and J, K is the bulk modulus of elasticity and J is the polar moment of inertia. Option D, C and J, C means rigidity modulus and the J means the polar moment of inertia. So right answer is E and I is the right answer. So flexural rigidity measure the stiffness of a beam, So we have the unit of Young's modulus as Newton per meter square and the unit of moment of inertia as meter to the power 4. So we will get Newton meter square is the unit of flexural rigidity. Next, question number 106. The bending moment at free end of cantilever beam carrying any type of load. Option A 0, option B maximum, option B minimum, option C maximum, option D equal to load. So the bending moment at the free end of cantilever beam carrying any type of load. So for cantilever beam we have three types of load. So cantilever beam subjected to point load at its free end, cantilever beam with UDL, next cantilever beam with UVL, that is uniformly varying load. So cantilever beam carrying point load at its free end, the bending moment diagram is as follows. So the bending moment diagram for a cantilever carrying UDL is as follows. For UVL as follows. So when a cantilever beam subjected to point load at its free end, then the bending moment at free end is always 0 and which goes on increasing towards the fixed end. Next, when cantilever beam subjected to point load, the bending moment at free end is always 0. So this is a linear curve, linear line, it's parabolic curve and it's a cubic curve. So here also when a cantilever beam subjected to UVL, the bending moment at free end is 0. So this is UDL, UVL, this is point load. bending moment at the free end of cantilever beam carrying any type of load. It may be point load, it may be UDL, it may be UBL. At the free end, the bending moment is always 0. So option A, 0, is the right answer. So next question, question number 107. The vertical distance between the axis of beam measured before and after loading at any point is called option A, deformation, option B, deflection, option C, slope, option D, elongation. So the vertical distance between the axis of beam measured before and after loading. So consider a beam before loading. So it's before loading. After loading, the beam will move to this position. The vertical distance of the axis of beam measured before and after loading at any point. So the vertical distance before and after loading at any point of a beam is called deflection. So it is deflection. So option B is the right answer. So deflection is the vertical distance between the axis of beam measured before and after loading at any point of the beam. So option A, deformation, it is the elongation of component due to loading. Option C, slope is the rotation of beam in terms of radian. Elongation means it is the increase in length, or it is tends to increase the length, is known as elongation. So the vertical distance between the axis of beam measured before and after loading is known as deflection. So option B, deflection, is the right answer. So next question, question number 108. For cantilever beam of length L and carrying UDL W kilonewton per meter, the deflection at free end is. So option A, WL cube divided by 8EI, option B, WL square by 24EI, option C, WL to the power 4 divided by 8EI, and option D, WL cube divided by 12EI. So for this question, we have to memorize the table as shown on board. We have to memorize this table for two types of beam, cantilever and simply supported beam. Cantilever with point load, cantilever with UDL, simply supported with point load, simply supported with UDL, and their corresponding elastic curve as shown on figure. So first, cantilever with point load, we have deflection as WL cube by 3EI, and for cantilever beam with UDL, the deflection is WL to the power 4 divided by 8EI. For simply supported beam with point load is given by delta is equal to WL cube divided by 48EI, and for simply supported beam with UDL, 5 WL to the power 4 divided by 384 EI. So one thing is clear that for UDL we have L to the power 4, and for point load we have power 3. So in the question he says UDL, so cantilever beam with UDL, so power has to be, so cantilever with UDL power is to be to the power 4. So option C, WL to the power 4 divided by 8EI is the right answer. So option A looks similar, but the power is 3. So for UDL, the power cannot be 3, it's always power to the power is always 4 for length. So from this table, it's clear that for cantilever beam of length L and carrying UDL, the deflection at free end is always WL to the power 4 divided by 8EI. So next question number 107. Short column fails due to option A cracking, option B crushing, option C shearing, option D buckling. So what is short column? If L by D ratio is less than 12, then it is known as short column. If L by D ratio is greater than 12, then it is known as long column. Long column, where L is the effective length of column and D is the lateral dimension. The ratio of effective length to its lateral dimension is less than 12, then it is known as short column. If the ratio of effective length of a column to its lateral dimension is more than 12, then it is known as a long column. The short column always fail because of crushing, and long column is always fail because of buckling. So in this question is asking about short column. The short column always fail because of crushing. So option B, crushing, is the right answer. Next question number 110. A column with highest equivalent length is option A both end hinged, option B both end fixed, option C one end fixed and other end is free, option D one end fixed and other end is hinged. So a column with highest equivalent length is asking the equivalent length. Which column has highest equivalent length if the following condition? So if both ends are hinged, or if both ends are fixed, or if one end is fixed and other end is free, or one end is fixed or other end is free. So we know that for a column with both ends hinged, effective length L is equal to capital L for both end hinged. So when both end hinged, then the length is, effective length L is exactly equal to length of effective length is exactly equal to length of the column. When both ends fixed, when both ends are fixed, when both ends are fixed, L effective length L is equal to 0.5 times of its length. So for both end hinged, L is exactly equal to, effective length is exactly equal to length of the column. So next option C, one end fixed and other end is free. One end is fixed and another end is free. So then effective length L is equal to 2 times of its length. Option D, when one end is fixed and other end is hinged. One end is fixed and other end is hinged. So in this case, effective length is equal to square root of, is equal to L by square root of 2, which means 0.707 times of length. So by looking, L is equal to exactly L is equal to 0.5 times, L is equal to 2 times, L is equal to 0.057. So by looking this value, we can easily say that a column with highest equivalent length, which column has highest equivalent length? So option C, one end is fixed and other end is free, has highest equivalent length. By this equation, we can say that option C, one end is fixed and other end is free, column has highest equivalent length. So option C, one end is fixed and other end is free, is the right answer for this question.